We're ready to talk about the derivative of the natural log function, and we can actually derive it. Let's begin with y equals ln x, and we'd like to have some expression for y prime. We'd like y prime equals something. Well, to discover that something, we move into the exponential form. You see, base exponent equals x. All right, now take the derivative on both sides. And let's just massage it a little bit. The derivative with respect to x of x is simply 1. And now divide by e to the y on both sides. And dy dx is just y prime. So y prime is 1 over x. And this y prime is the same y that we started with, in the logarithmic form. And this situation leads to an incredibly powerful tool for us. If y prime is simply 1 over x, look at what it means. It means that if f of x is ln x, then f prime of x is 1 over x. Okay. But the real power comes as we introduce the chain rule to this situation. You see, using the chain rule idea, it's the notion that f of x is some natural log of an expression involving x. Now that expression involving x is designated with, or the notation for it is u. So this is just ln u, all right, an expression involving x. F prime of x, then, using this chain rule idea, is f prime of u times u prime. Now, I could be using du dx over here, but I like this kind of notation because it's a little cleaner in my view. So f prime of u times u prime. But f prime of u, you see, is just 1 over u, because this is a natural log situation. So this is 1 over u times u prime, so this consolidates to u prime over u. A very simple idea, and a very powerful idea as well. Let's take a look at a few problems. Suppose we have f of x is ln of this expression. You see, and all we do is write it in its, the derivative is u prime over u. So the u prime, the u is the expression, you see. And u prime, the derivative of the expression, is 2x. And the expression itself is x squared plus 1. And that's all there is to it. And then in other situations, we just bring to bear our product rule, our quotient rule, and everything else that we learned before. And for example, we can use the product rule in this problem. F of x is x times ln x. Well, we have a couple of factors here, so we're going to use the product rule. And to set it up, it is that the derivative is first factor times the derivative of the second factor, then second factor times the derivative of the first factor. And that's all there is to it. Now think in terms here of the u prime over u. The u business is simply the x. So it is u prime, that's simply 1, and u is x. So x times 1 over x is 1, and over here we have ln x times the derivative of x is 1, so this is ln x, so 1 plus ln x. Here's one that's a little more complicated. Same idea, though, using the product rule, but it's a little more complicated, and it's important that we just resort to organizational skills to deal with that. But it's really not a big deal. It looks much more complicated than it really is. Here's the g function, and we want its derivative. So the derivative of g is, now separate your thinking, here's a factor, here's a factor. Using the product rule, it is x cubed times the derivative of this rascal. And then it is this factor times the derivative of the x cubed. So we slide back over here, and away we go. We have x cubed times, now it's u prime over u. So think about u prime, here's u prime, the derivative of this is 3x squared. And then the u part is the x cubed minus 5. And then over here, similar idea, it is this factor times that. Now when we take this derivative, we're not going to write it to the right of this parenthesis because it'll look like the natural log of a product. So we're going to write this, the answer, the result of this, to the left side as a factor. But the derivative of x cubed is 2x squared. So it's 2x squared ln x cubed minus 5. And now it's just a matter of cleaning up. The x cubed times this numerator gives us 3x to the 5th power. And this then is our final answer. It's a relatively simple situation. Actually, it's not a final answer. I almost made a mistake here. Let me write this correctly. I forgot to write the ln here. But once I pop that in, this then is our final answer. Here's another one. Now this one illustrates the need sometimes to go through a rewriting process before we actually find derivative. It is this, that we have ln square root of x plus 1. We'd like to clean this up a little bit, write it in another form. We think of the square root business as a fractional exponent, so this is x plus 1 to the 1/2. But aha, we can use the power property here and write this as 1/2 ln x plus 1. And now we bring to bear on this the product rule that we looked at before. So it's 1/2 times the derivative of this, and then this times the derivative of 1/2. Well, that's going to go out because the derivative of the constant is 0. So that term disappears. And now it's just a matter of dealing with this. Now in this environment, you may wish to write a step like this that I've written here. I didn't write it on the previous problem, and I could have. But just to keep things straight and to remind us of what we're doing, we might do something like this is 1/2, and the derivative of a natural log expression is the derivative of the expression over the expression itself. So we're just emphasizing that idea here. And the derivative of x plus 1 is 1, and the expression itself is x plus 1. And now we just rewrite for our final answer. Here's another situation where it's valuable to rewrite before we go into the derivative. If f of x is this, then we rewrite by expanding. We have a product here, so it's the natural log of one factor plus the natural log of the other factor. And here we get to use the power rule. This is 2 times ln of this expression. And now we can go through and find the derivative. The derivative of ln x is just 1 over x. But here we need to use the product rule. And remember, it's 2 times the derivative of this. And the form that this takes is u prime over u. And for the other one, we become accustomed to the idea that if we have a constant involved as one of the factors, then the derivative of this constant is 0. So we have 0 times another factor that doesn't really make any difference here. So that goes out. And now the u prime over u, the u part is the x squared plus 1. So u prime is 2x, and then the u is the x squared plus 1. And now we just clean it up. 2 times the 2x is 4x in the numerator, and here is our final answer. Here's a word problem dealing with this situation. 200 college students took French in their freshman year, and then they were tested ever so often to find out how much French they retained. And so this becomes kind of a memory model, this equation does. P stands for the test score in percent, T is time in months, and here is our memory model. And we'd like to find out the rate at which the average score is changing after 1 year. Now, rate of change is all about derivative, so we find the derivative of this P equation. P prime then is, and we go through and we think, well, the derivative of this is 0, so it goes out. The derivative here, we are going to use the product rule, and it's this times the derivative of that. Oh, the derivative of that is the u prime over u. And that's what I've written right here. And the last term is going to go out. So it's u prime over u. Now the u prime, the derivative of t plus 1, in terms of t now, is just 1, and the u business is the t plus 1. So we have this. And now we just pop in the information that we want for the period of time. 1 year, well, that's 12 months. Remember, t was in months. So that's 12 months. So we pop a 12 in here. 12 plus 1, that's 13. 1 over 13 times this. We find p prime to be negative 1.2. So the decline, the rate at which the memory is being lost is negative 1.2% per month at that point in time. Take a look at this. Suppose we want to evaluate the log of 8 in base 2. And it's pretty easy to do if we just set this equal to some letter like x and then solve this by changing its form to exponential form. Base exponent, so this is 2 to the x power, is equal to 8. Sort of by observation, we can tell that x needs to be 3 in order for this to be true. But a way of rewriting to make sure of that is to rewrite so that the base on both sides is the same. And you see, if we know that what's over here is the same value as what's over there, and we have 2 to some exponent here is equal to 2 cubed. You see, the bases are the same, so the exponents must be the same if these two are to be equal. So in that circumstance where we can make the bases alike, we can set the exponents equal to one another and say here that x is equal to 3. So x equals 3 is our answer. All right, in a similar way, we can find this value. Now, you might be thinking, well, gee, isn't there an easier way? Well, there is another way, and I'll show it to you in a few minutes. But if we're going to solve this sort of algebraically, we can set this equal to a letter and then base exponent, so we have 3 to the x power is equal to 81. Now, can we rewrite this so that the bases are alike? Sure, we can. This is 3 to the x is equal to 3 to some exponent. Let's see. 3 times 3 is 9, times 3 is 27, times 3 is 81. Oh, this is 3 to the 4th power. If the bases are alike, then set the exponents equal to one another and find an answer. Now, this works fine as long as we can make those bases look alike, but what happens if we get to a situation like this? Log 3 and base 2. When we try to make the bases look alike, we run into a sort of a brick wall. This is 2 to the x power is equal to 3. But we can manipulate this in a way and find a method for dealing with this situation. And we can do it by applying logarithm on both sides. Now, I'm going to apply natural log on both sides because that's what we're accustomed to dealing with. So ln 2 to the x is equal to ln 3. And look at what happens. We have a situation here where we can use the product rule. So this is x ln 2 equals ln 3. Now, ln2 and ln3 are just numbers in the calculator. So this is a coefficient of x over here. So all we need to do is divide on both sides by that coefficient of x, and we'll solve that for x. And so I can write then that when I divide on both sides by ln2, this ln2 goes out and we have x. And on the right, when I divide by ln2, I get ln3 as the numerator and ln2 as the denominator. Now, I want you to notice something here between these two forms. Oh, actually, it's between, I'm sorry. It is between these two forms. See, x equals this, and x is equal to this. And notice that log 3 and base 2 is the same as ln3 over ln2. And it turns out that this pattern can become a change of base formula. And we can go through all of this process, and we can actually punch the calculator to find this, this actual value. And x turns out to be approximately 1.585. So 1.585 is the exponent on 2, which will give 3. All right, but the idea here, more generally, is that we can change bases like this. If we have the logarithm of a number in any base, then we can change it to something that we can deal with the calculator on by just saying it's ln b over ln a. Now notice the use of the b and the a over here in this change of base relationship. Now, because common logarithms also appear in the calculator, we may want to use common logs to make the calculation, and the change of base works equally as well. We could say then that the log of b in base a is log b over log a. You see, and this base over here can be any base that we want it to be. It's kind of convenient, though, to make it base 10 if we're looking for a value here and we want to use the calculator. Now, let's use that idea here. Log 6 in base 3. Well, going through the change of base idea just very quickly, this is ln 6 over ln 3. You see, and now we just punch the calculator to find the value to be 1.631. You see, so it's just that easy. Let's talk about some of the derivative formulas that we have up to this time. You know, I don't want to suggest that we need to memorize these. I do want to suggest, though, that we want to know about some of them, and we want to be able to conjure up the others from the ones that we know about. You know what I mean? We just kind of, we use some situations that are etched in stone, and we sort of extrapolate from that to understand other relationships. Here's what I mean. We know that if f of x is e to the x, f prime of x is e to the x power. Okay, great. We can prove that, and some of this is going to be new to you, but if f of x is a to the x, now notice the base is something other than e. You see that a to the x, the derivative is ln a times a to the x power. ln a times a to the x power. Wow. All right. We also know that if f of x is ln x, then the derivative is 1 over x. But what if we're not talking about ln x? What if we're talking about the logarithm with a base other than e of x? You see, how does that go? Well, it turns out to be 1 over ln a times 1 over x. Now, there's some similarity here, some refer back. I think this tells us two things, that we can kind of compare this form with that form, and it also tells us that it's a lot easier to work in the natural logarithmic area and the area of e as the base of an exponential function than it is another base, you see. So the ln idea has great power now that we see these kinds of forms. Now, from here, you might be thinking, well, gee, there are more complicated situations than this, and certainly there are. And those complicated situations are when the x up here is replaced with some expression in x. And that's true for all of these, that we can replace x with a u being an expression involving x. And what we find out, though, is that the form for derivative is remarkably similar to these. I mean, if you just take all of these and replace x with u, and then tack on a u prime at the end as a factor in the derivative form, then you've got it. You see, and that's the pattern that I want you to notice. For example, now I've written them all over here, that e to the u is e to the u times u prime. All right, it's similar to this over here. The e to the x was e to the x. Now remember, I said replace x with u and then tack on a u prime factor. So it's that same idea. And if we have a to the u, some constant other than e, to an expression in x, then it's ln a times a to the u times u prime. Now notice the similarity between these two. See how similar they are? Replace x with u and tack on a u prime and we have it. All right, ln x, over here ln u. Now we just talked about this. The ln u, the derivative is u prime over u. Now over here we had 1 over x. And you replace the x with a u and tack on a u prime factor and we have this. And then over here we go with a more general logarithm, the logarithm of some expression in x to some base other than e, and we have 1 over ln a times 1 over u times u prime. Looks complicated, but it's related back to this. 1 over ln a times 1 over x, you see, you replace the x with a u and tack on a u prime factor and we've got it. So there are relationships all around here to help us with these.